Right, today we're going to discuss lab 9, where we focus on how to handle floating point numbers. As we have discussed in the lecture, floating point numbers may not be able to represent it precisely using binary representation, and hence there will be rounding off errors. Now we're going to look at a library file system and another library reward systems. We are going to perform some numerical computations involving floating point numbers. Now let's start with library file system. So if you go to a library, for example, the Columbia County Library, so if you return the book late, the book that you borrow late, you will incur a fine. So the fine is 20 cents per day late. Okay, so now you are asked to create a program that make this library file system where, given the number of days late in returning the book, you are asked to compute the total fines. So we assume the number of days late is an integer. Okay, so we have created a variable called fine, which is initialized to 20 cents. So the unit is $0.2 means 20 cents. Okay, now I'm going to ask user for input, which is number of days late. So days late is equals to user input. So input, enter the number of days late in returning the book. Okay, and we assume user and always enter integer for simplicity. And then we compute the total fine is equals to the number of days late. For each days late, you're going to incur the fine of 20 cents. So it will be the value of fine. Okay, so the value of fine is type float. You can check it here. Type of fine is float, is initialized from 0.2, which represents 20 cents. Right? Then you can print. So the total fine is, which is the value of total fine, which is the variable that we use to compute or store the value of the computation of days late times fine. So here's example, say 3. Then we get 3 days late, and each day you incur 20 cents. So in total, you incur 60 cents of fine. But as you can see, when we represent the fine as 0.2, fine is of type float. And 0.2 is a floating point number that cannot be represented using binary representations precisely. And hence, when we compute the total fine by multiplying days late with fine, we get 0.60 with a bunch of zeros and with a last digit of 1 here. So you can see that this is not precise. We should have a precise value of 60 cents as a total fine, but we get this value instead. Okay, so we see that there is a routing of error since 0.2 is a floating point number that cannot be represented precisely as binary representation. Okay, so it's the same as 0.1 that we discussed in the lecture. 0.1 also cannot be represented precisely as binary representation as well. The idea is to see that if 0.2, so this is because if 0.2 can be represented precisely as binary representation, then 0.2 divided by 2, which is 0.1, can also be represented by precisely as binary representation as well. So if 0.2 can be represented precisely as binary representation, that means what does it mean is that it can be written, so it can be written as some value of 0 and 1s. So A0 times some combinations of digits multiplied by digits in 0.1 and digits multiplied by some powers of 2. So some I equals some combination of A I to the power I, or AI is in 0 and 1, is either 0 or 1, and I is an integer. Okay, it can be negative integer. So if it can be represented precisely as binary representation, it can be written in this form. This means sum of A subscript I to the power I, where A subscript I means is a variable, is of 0 of 1. Okay, so it means it can be written as a sum of some digit, a sum of powers of 2. Okay, this power of 2 can be where I is positive or negative. All right. In this case, it has to be negative because 0.2 is less than 1. All right. Now, if it can be written in this form, and if I divide by 2, I will also get the same, I will get the same representations, a similar representation. Then 0.2 divided by 2, which is 0.1, can also be represented precisely as binary representations in this form as well. Okay, where now is divided by 2, so I have I minus 1. All right. But we know from the lecture, 0.1 cannot be represented precisely as binary representations. Hence, we conclude that 0.2 cannot be represented as precisely in base 2 or as binary representations. Okay. So this is remark. So it's something extra. So we know 0.2 will give us 0.2 as a floating point number, give us rounding off error, which means 0.2 cannot be represented precisely as binary representations. And the following gives you a formal proof why 0.2 cannot be represented precisely. Because if it can't, that means it can be written in this form where it's sum of some power of 2. And if you divide 0.2 by 2, which will give you 0.1, the representation is remain as some combinations of a sum of powers of 2 as well, which means 0.1 should be able to represent it precisely as binary representation. However, we have seen that it can't be represented precisely in the lecture, and hence we conclude that 0.2 cannot be represented precisely in base 2 as well. Now you're thinking, okay, how should we fix this? If we want precise computations, maybe we can round it to 2 decimal points, okay? Because as you can see here, the arrows is towards the ends. It's kind of precise up to some digits, some digits here, up to some number of decimal points. And we have seen that in Python, actually it depends on the system. In Python, it can be precise up to 53 bits. So up to certain digits, it will be precise. So for example, we can try with round to 2 decimal points. Okay, so we can, for example, try to round it to 2 decimal points. Right, and then let's print it now. Say 3, and now I'm rounding it to 2 decimal points. It becomes 0.60. we've omitted 0 here, which means now we have a right value for this number of books. However, we're not sure whether rounding to 2 decimal points will always give us no rounding of error. It's possibly that for some number of books, it could give us a rounding of error, even if you round it to 2. I would think that it's very unlikely, because the error, the rounding of error for 0.2 shouldn't be that big. So if you round it to 2 decimal points, it shouldn't give us any errors. However, if you want to be very precise in your computation, especially when you talk about fines or money, you want to be very precise. You don't want to be assuming that rounding to 2 decimal points will not give you any errors. You want to be very precise, especially in banks or in fine system where you involve money. You have to be very precise. You can use what we have learned in the lecture called decimal. Then every calculations will be done correctly as in mathematics. So now we're gonna use decimal instead. Okay, so we're gonna import the library decimal, and we import the type called decimal. It's an object type. Okay, so now my fine is no longer defined as a floating point number. Rather, it will be defined as type decimal. All right, so fine now will be equals to decimal with a string 0.220. Okay, so let's run this. Now, if you want to check the type of fine, you see that it's a type decimal, right? So any computation involving type decimal will give precise calculations. So now I have days late times fine. Let's see. Let's give it a try. And now I get a precise value, which is 60 cents. Okay. In what we did is that we convert, or we represent a number 20 cents as a decimal type, which will give us precise computation. However, as we have also experiments in the lecture, using decimal for computations, it's very time consuming compared to using float. So if we want to avoid rounding of error, there's another method where we can convert it to its equivalent integer. So remember earlier on, fine is 20 cents, where the unit is dollar. Okay, so 0.2 is equivalent to 20 cents. So instead of writing it as a floating point number, we can change it to unit is cent. Okay, so in cents, fine will be 20 cents. Right, so instead of 0.2 as dollar, which represent 20 cents, we write fine as 20, where the unit now is cent. So now fine is an integer. Okay, so integer can be represented precisely as a binary form. So integer can be represented precisely as a binary form, binary representation. Okay, hence there is no rounding of error. Okay, so and it's also faster. However, 20 is a larger number, for example. So now we can compute everything using integer now as a type int. So type fine is int, all right? And we don't have any rounding of errors. We come there, total fine is this, okay? Now say 3, and we get 60, but we need to be precise. Say total fine is 60 cents, okay? So let's try. So now the total fine is 60 cents. So it's equivalent. So we have 0.6 as dollar, and here we have 60 cents. So they are equivalent. $0.6 is equivalent to 60 cents. And here, by using int, I don't have to worry there is a rounding off error, and I don't have to use a decimal because it's slow. All right. So I have this. However, the downside is if you have, for example, larger values of larger fine, say I give 100, then you have the total fine is 2,000 cents. So you want to tell the user that you incur a fine of 2,000 cents, which is very difficult for the user to understand it. What does he mean by 2,000 cents? You might want to convert it to its equivalent integer or equivalent dollar unit before you display to the user, because 2,000 cents, the user has to do a manual computation by themselves to convert into, say, $20. Okay, so as a remark, if the fine is say 2,000 cents, all right, the user has to do manual computation to figure out that, you know, the fine is $20. Okay, so that's the downside of it. And what we can do is that we can do, before we display it, you convert it into its equivalent dollars. So before we display the fine, the total fine, we can compute its equivalent unit in dollar. Okay, so this is an extra step. All right, so instead of writing just as cents, we can convert it into its dollar form. Okay, so $1. So note that $1 is 100 cents. So we don't want, we are fine with 60 cents, 70 cents, but 100 cents, we want to convert it to its equivalent dollars. So it's $1 is 100 cents. So before we keep the total fine as an int, all right? And then when we display it, we can display, we divide it by 100. Okay, we divide by 100 so that it becomes a unit of dollar. So we try now, for example, 100. If that 100 days left, it should be $20. Okay, so we can, for example, more precise dollars now. Okay, so now is what did I do? 100 here. So it should be $20. All right. So all the previous code, it should be also more precise. For example, here should be dollars. If the unit is dollars, we will write it as dollars as well. Okay. So now we have a system that use precise computation because everything is done in int. Because our file is int, there's no rounding off error. And when we display to user the file, is also we compute everything still in int, but when we display to user, we divide it by 100 to get it into dollars. Okay. Now let's look at the second example. So in this example here, the fine is 20. It's a 20 cents. And which we already know that it cannot be represented precisely, and hence there might be a rounding off error. So what if we change the fine to 25 cents instead? Now, when you create a system like this, you need to think 25 cents is a floating point number, all right? So know that 25 is a floating point number. However, 0.25 can be represented precisely in base 2. In particular, 0.25 is just equals to 1 over 2 to the power 0.25 is it's basically 1/4, which is 2 to the power minus 2. Okay, so it can be represented by some powers of 2, or some linear combinations of power of 2. All right, so we know 0.25 can be represented precisely in base 2. So when you store 0.25 as a floating point number, there will be no routing of error because it can be stored precisely. And hence, in this case, we don't have to worry about routing of error. We don't have to say, should we try to round to 2 decimal points? Or should we be very precise and use a decimal library? Or convert it into its equivalence integer format, where from dollar to cent. We don't have to worry about it. We can just write it as 0.25 and compute it as it is, because we don't have any worry of routing of error. So now my phi will be equal to 0.25 as type float, where the unit is dollar. So $0.25 is equivalent to 25 cents. All right, and I don't have to worry about converting it into its equivalence integer forms, or using decimal to be more precise, or rounding it to 2 decimal points, because everything will be precise. So if, for example, I type 3 days late, it will incur 75 cents. So it would be in terms of dollar. Okay, $0.75 is 75 cents. Okay, so when you are asked to create a system in the future where involves computations numerical computations, floating point computations, first thing you need to think is, how do we represent these floating point numbers? Will it give us routing of error? If it's not, we can represent it just as usual as a floating point number. If it is going to give us a floating point error for numbers such as 0.1 and 0.2, then we need an extra step. Whether you want to round it to 2 decimal points and take the risk that it might give us routing of error. It might not give us a risk of rounding of error after rounding to 2 decimal points. Or you want to be very precise, very accurate, you use decimal. Or you want to not using decimal because it's slow, or you don't have the library decimal, you can convert into its integer forms, equivalence integer forms. Instead of unit as dollar, it's unit as cent. So these are something that you need to think of when you create a system. Now let's look at extension of this system here. Say the fine is still 20 cents per day late, so we know it can't be represented precisely. So we know that we have multiple options here. We can either change it to integer equivalent form or use a decimal. And now I extend it a little bit, where for the first 7 days, the fine is 20 cents, but after 7 days, the fine will increase from 20 cents to $1. Okay, for example, if the number of day late is 6, then the total fine will be $1.20. If the number of day late is 8, then the total fines will be 7 times 20. That will be the first 7 days total fine, plus the remaining days that you return late will have $1 charge. Okay, the remaining day will be 8 minus 7 if your number of days late is 8. So 8 minus 7 times 1. So the total cost will be 1.4 plus 1, which is 2.4. So $2.40. Okay. So here, change. So this will represent the number of days late. Just being consistent here with the above, where I put days late here. All right. So now how do we write this program? So here, we're going to do a standard version. And here, we're going to do fine equals to 0.20. So this will be the fine. But we have 2 different fine. One is 20 cents and one is $1. Okay. So we have a small fine of 20 cents. We have a larger fine of $1. Okay, and suppose because it's deal with money, we want to be precise. So we're gonna do decimal here. And remember, we need to make it a string first. Okay. So now my small fine is of type decimal. My large fine is $1 because it's an integer. I don't have to convert into decimal. So these are both my fine. And this, I ask user for input where I convert it into int. So I have a days that is type int. And what will be my total fine? So early on, my total fine will be just the number of days times fine. But now I have two different fine. Okay, we will have a small fine and a large fine. So it will be the first 7 days will be the small fine, and the subsequent days we will incur large fine. So how do we go about doing this? So we need two different cases. Okay, so there will be two different cases. If days late is less than or equals to 7, all right, then the fine will be the same as before. Total fine will be the days late times small fine. All right, so small fine is 20 cents. For each day that you incur late, you will multiply it by this small fine for the first 7 days. Else, right, if days late is more than equals to more than 7, is greater than 7, then we know the total fine will be equals to 7 times small fine. Okay, the first 7 days will be we will incur, for each day you will incur small fine, and then plus the remaining days will incur $1. Okay, so the remaining days will be the number of days late minus 7 times large fine, right? So if it's less than equals to 7, you will just do days late times small fine. Otherwise, if your number of days late is more than 7, the first 7 days, each day you incur small fine. The subsequent days, the remaining days, you will incur a large fine. So the remaining days will be days late minus 7, and each day you incur large fine, right? So let's try for example, enter the number of days late in returning the book. Say if it's 3 days, it's still $60, 60 cents. $0.6 means 60 cents. So it's the same as before, good. But if you say it's late by 8 days, okay, it will be $2.4 or equivalently $2.40. All right, let's look at the final fine system where it's the same as before. We have incurred 20 cents per day late for the first 7 days. After 7 days, the fine will increase from 20 cents to $1. And now we have one more step where one more requirement is that the maximum fine is kept at $20. We don't go beyond $20. So here's an example. If the day late is 6, okay, so it's within 6 days, then the total fine will be 6 times 20, 0.2. 6 times 0.2 will be $1.20. If the days late is 8, okay, then the total fine will be 7 times 0.2 plus 8 minus 7 times 1, which we have seen is equals to 2.4. So it will be equals to 2.4. Okay. Now, if the number of day late is say 30, so late by 30 days, well, it will be exceeding $20. So, but we cap it at $20. So the total fine is $20. So the total fine is $20. So the total fines. So if you use the previous calculations, so the fine is 7 times 0.20 plus the remaining days, which is 30 minus 7 times 1. Okay. But this, which exceeds 20. So the total fine is kept at 20. Okay. So this value here, 7 times 0.20 plus 30 minus 7 times 1 will exceed $20, and we only do the maximum cap of $20. So the total fine displayed to the user is actually 20. Okay, so let's do this. So again, we have a small fine and we have a large fine. Right? And we have days late. If the days late is less than or equal to 7, we have this, else, this, and so on. However, we have this additional requirement that the maximum fine is kept at $20. Okay, so how do we do this? So multiple options. Okay, say if total fine is more than 20, okay, then you reset total fine to just 20. Okay, so if the total fine that you calculated exceed $20, then we don't charge user more than $20. The total fine is still kept at $20. So for example here, if I late by 30 days, I'd say the total fine is $20, even though your computation show that it's more than $20, but because we have this requirement that we don't exceed $20 fine, no matter how many days the user return late, if the total fine calculation show that it's more than $20, we just find the user $20 only. However, if it is less than that, for example, earlier on we have 10 days, it's $4.40. If it's 3 days, for example, it's 60 cents. Okay. Now, this is one way to do this using if and else statement. Another way, for example, so this is one way. And second way, for example, is that you can just do total fine is equals to this, and you just do the minimum of the value that you computed using the calculation of small fine and large fine and 20. So what you do is that, suppose like this, okay, you calculate the total fine, and then you do total fine of mean between the total fine and 20. Okay, so this will take the minimum between total fine and 20. So if total fine is exceed 20, so it will take the minimum between total fine and 20 will be 20. Okay, so it's basically doing the same thing, except that I use a built-in function mean to help me to figure out which one is the minimum, either the total fine or 20, rather than explicitly write an if statement here. So it will give me, for example, the same answer. Okay. For example, here is 30, it gives me $20. 30 days late, and the same thing here, 30 days late is also give me $20. So they are doing the same computation, except that I use the built-in functions to help me to do the check of which one is minimal between total fine and 20. And here is that I run an if statement instead. Okay. Now, is this the best way to do it? Right. So note that here I still do computations. Okay. Here I still do a computations. So if it's 100 days, I still do 7 times small fine plus 100 minus 7 times large fine. But you already know that. So remark here, we know the maximum fine is capped at $20. We actually so we know exactly how many days of fine, how many days late that for which we will have a fine that is $20. So exactly how many days that our fine will be $20, okay? By computations, for example, we know 30 days, we will have $20 because 30 days will give us total fine that is more than $20 and we kept it at $20. right? So we can compute this maximum number of days. How many days late for which so we can compute the maximum number of days late for which the fine is less than $20. Okay, so then if the number of days late exceed this maximum number, we immediately say the fine is less than $20. We don't have to do. So if user enters a number that exceeds this maximum number, then we don't have to do any computation, but display that, and immediately display that the total fine is just $20. Okay, so here, whatever user enter the value, you do this computation. But for a certain number of days, the maximum number of days, you actually don't have to do computation at all, because if the number that user enter exceed this maximum number of days late, you know that it has to be $20. You don't have to do computation. You don't have to do this total fine equals to some value that is more than 20 and then take the minimum of it. All right. So you can pre-compute this maximum number of days. So we just need to pre-compute this maximum number of days late. So how do we pre-compute this number of days late? So we can say maximum days late be a variable that represents the maximum days late for which the total fine is less than 20. Okay, and we want to compute this value of maximum days late. Okay, so the total fine is this. Okay, so by formula, okay, so we have the total fine is 7 times small fine plus the number of days late, so maximum days late minus 7 times large fine must be such that it is less than, should be less than 20. All right, so now you want to find what is this maximum days late. So you just need to compute the maximum day late, the maximum value of mixed days late for which this formula here is less than 20. Okay, so this is easy. So you just shift everything. So this is, so hence maximum days late is equal to, so this is just solving inequality. So this is equivalent to solve the following inequality. So this is equivalent to solving the following inequality, which is 7 times small fine plus maximum days late minus 7 times large fines, less than equals to 20. All right, so this is the inequality that we want to solve. All right, this is the inequality that we want to solve. So mathematically, to solve this is equivalent to, so max days late is equal to, so 20 minus 7 times small fine. All right, and the whole thing divided by large fine. All right, and then the whole thing plus 7 And that will be our computation. So this is just solving this inequality here. So small phi is 0.2, large phi is 1. What is the value of maximum days late? The largest value for maximum days late, so that this inequality is satisfied. So you know it from your high school. You just take out maximum days late, must be less than equals to 20 minus 7 times small phi divided by large phi plus 7. So this is just high school calculations. Okay. So we do this computation. So maximum days late is equals to this that we have already that we have already written it down. Okay, we have this. All right, so let's see what is this value here. Print max days late. So we have 25.6 days. So again, it means that when the maximum value for which the maximum days late can be, where it will incur cost that is less than 20 is 25.6 days. So we don't, but for day, we want it to be integer. There is no half day. It's either 1 day, 2 days, which must be integer value, whole integer value. So what's the maximum days late? We need to make it into an integer. So we use import math. Okay. So we take the highest integers, the smallest integer greater than 25.6. In this case will be 26. Okay. So you can do so for any value using math.floor. So this is built-in functions that return the ceiling of x as an integral that is the smallest integers greater or equals to x. So for example, math.floor of 25.6 will be 26. Okay, so after 26 days, it will so it means that after 26 days, the fine will be $20. Will be exceeding $20, but we always kept at $20. So the total fine displayed to the user will be $20. So the maximum days late here will be math.floor of this. Okay, now we have our final code of computing maximum days late, which will give you 26. Now our final code will be in this format here. So this is pre-compute and save to the system. And now we ask user for the number of days late. Okay. So we have, this is our full code. So we have here the fine, and based on the fine and the largest cap amount is $20. So here I can, for example, say maximum fine. All right. So I like to write everything as a variable here because I don't want, if in the future, the system change from maximum 5 to 20 to $50, I don't want to look for all occurrence of 20 and change it to 50. I will just change it here. So it's important that you don't write absolute value most of the times, and instead write as a variable. In the future that you want to change it, you just change in one place here. Okay, so now I have all these value. These are given at this moment. It might change in the future, but these are given, and I'm gonna pre-compute the maximum days late, which is 26. And then this is my system that asks for user for input. If the days late is less than or equal to 7, I compute using small phi. Else, I'm going to check if the days late is less than maximum days late. If the days late is less maximum days late, oh, actually, I make a mistake here. It should be floor, not it should be floor, not ceiling. Okay, so which means because after 20, exactly starting from 26 days onwards, it will be $20. All right, and starting for 25 days and below, it will be still less than $20. So the maximum days late for which you will incur fine that is less than or equals to $20 will be 25. So I should use floor. Should be the largest integer less than the computed value. Okay, so I'm gonna write it out here. So if users return the book after 26 days, the total fine is $20. If user returned the book within 25 days, the total fine is less than 20. Okay, less than or equal to 20. Right. So we should use floor instead. Okay, so if the days late is less than or equals to maximum days late, we will compute the total fine using this formula. Else, we don't have to compute anything. Else, the total fine will be equals to the maximum fine, which is initialized to $20. All right. So let's check here. So if it's 30 days, we get the total fine is $20. And notice here the difference is that we did not compute the total fines of 30 days using the for a bit like the previous version. Rather, we check whether days late is it less than this maximum days late. So 30 days is more than 25, so it will cap it at $20 maximum fine. Okay. So of course, this is a better version because we don't do large computation. Previously, we will do large computations here, especially when days late is very large. All right. So this is done by pre-compute. The maximum days late corresponds to the maximum fine. Now, as an exercise, you are creating a different system. Now, instead of fine system, we are creating a reward system. So you are to encourage a user to read, the following reward system is in place. For each book a user borrows, a reward of 0.1 point is given. Write a program to ask user for the number of books that the user has borrowed and display the total rewards. So we always assume user enter an integer. So for the first exercise, you compute the reward using float. So reward point is actually equals to 0.1. And then you compute the total reward based on user input, and you round the total rewards to 2 decimal points. Now, we know that 0.1 cannot be represented precisely as floating point number. So if you want it to be precise, we can compute the reward using the library decimal. So the second system, you can make it you're gonna do reward point is equals to decimal 0.1. Okay, and then you will get precise computations of the total reward point. So you should continue. This is to do. You're gonna ask user for input, compute the total reward, and display to the user what is the reward. Okay, so this is for you to do. So to do, and here to do as well. Now the system tree using decimal can be slow. Can you convert the rewards into its equivalent integer? So now the reward point is not decimal, it's not 0.1, but it's 10th. Okay, so it's 10th, but so it's 10th. So for example, so 10th is equivalent to 0.1 point. Okay, but when you display to the user, okay, when display to the user, convert it back to the original point system. Okay, so here to get 0.1 to 10, you multiply by 10. So you compute everything, total reward equals to something. After you compute it, when you display to the user, you divide it by 10. Okay, so in other words, when display the total reward, divide the result by 10. to get back to the original unit. All right. And the last system, after with just a minor notifications, after 10 books, the reward will increase from 0.1 to 0.2. So again, there are two reward system now. So we have small reward is 0.1. So 0.1 cannot be calculated precisely. We can make it precise using decimal. And then you have a large reward, decimal 0.2. All right, and then you compute using this small reward and large reward based on the number of books the user has borrowed. Okay, so again, this is to do. Right, so this is also to do. All right, now the final system is that we kept the reward at 100. Okay, the maximum the reward the user have is 100 only. So the same thing, you can do these computations here, where you do, instead of mint, you do max of the total reward with 100, or you can pre-compute the maximum, the minimum number of books that that you need to borrow in order to get the rewards of $100. So you just borrow that amount and you already have the rewards of $100. So you can, so this is again to do following the sample code above. Right? And that's all for today. Thank you.